Should I start? Okay, so this is welcome to the third and final of my talks. So part one, as you hopefully remember, was an introduction to, a very brief introduction to CFT and VOAs. Part two was an introduction to rational VOAs. And part three which is basically today's talk, will be an introduction to Log-CFT. So again, roughly speaking, a Log-CFT or Log VOA are VOAs, rational VOAs are where everything goes well, and Log VOAs are where things start to fall off the wagon. So to remind ourselves of what a rational VOA is, I never defined what a rational VOA is, but I'll state several of its properties. So it's a VOA, which we all know all about, which has finitely many simples. It's semi-simple. So as you know, what that means is any module will be a direct sum of simples. It has duals. It has a fusion product or tensor product. What am I forgetting? Well, it has any module. It has L naught, the Hamiltonian here, the energy operator, one of the basis vectors in our Virasoro algebra representation, is diagonalizable in any VOA, and in a rational VOA, all the modules. It's diagonalizable on all the modules. The VOA, the modules of your VOA also carry a representation of the Virasoro. And so we can write this as we can decompose M into a sum of eigenspaces for L naught, for the energy operator. So we can write it like this. This is meant to be an H. This is meant to be an H plus 1. So this will be a simple module. So the energies go up by 1. Each one of these is finite dimensional, and so you could talk about the graded dimension, is what you should call it. But unfortunately, heathens came long before the more enlightened people did and call this the character of the VOA. So what this is just the graded dimension of this. You sum over all n of q to the eigenvalue. So this will be, I guess, h plus n in this notation, times the dimension of that homogeneous space, that graded space, which is h plus n. Okay, well that's fine, that's wonderful. But of course these have properties, and these are modular forms, or more precisely, they're vector-valued modular forms. The span over the complex numbers of these finitely many characters is closed under the action of SL2Z by fractional linear transformations. So for example, you have this relation. So if your favorite module, you can substitute in minus 1 over tau. That corresponds to the matrix 0, minus 1, 1, 0, an element of SL2Z. And this is going to equal, as it does for any of these fractional linear transformations, it's going to give you a linear combination of of these other characters, the other greater dimensions. So it'll be a sum over all, let's call it big N, of chi big N's. And then the coefficients of this expansion is the S matrix. And this is the S matrix. Oops. This is the S matrix that gives you, that you plug into Verlinda's formula, and it gives you the fusion coefficients. So you take tensoring or fusing two modules together is, of course, because it's semi-simple, decomposes into a sum of simples, and so you get fusion coefficients. So the fusion coefficients, I'm not going to write it down. I'm sure you've all seen it too many times anyways. It's a miraculous formula, and it looks like this. By the way, it's a miraculous formula, but finite groups have a version of Verlinda's formula, so it's not magic. Similar-ish theories all have a Verlinda's formula. So, okay. Now, there's a couple more things I want to add into this before we can dive into the log story. One of them is we dropped some point fairly early in our introduction to CFT. I claimed that we can focus on the holomorphic part of your CFT, or you decompose your CFT into right moving and left moving, or holomorphic, anti-holomorphic, or whatever words you want to use. And that holomorphic piece and that anti-holomorphic piece give you your VOAs, give you your chiral algebras. And so at some point, you have to combine these two and get back your full CFT. So your full CFT has two chiral pieces, has two chiral algebras, as we already know. And a chiral algebra, our word for it is VOAs. So it has two VOAs. These can be isomorphic. Or in the heterotic case, they won't be isomorphic. And then, but we need to splice. So let's call these VOAs, just for the heck of it, let's call it VV bar. And then VV bar, or rather the tensor product of these two, acts on the Hilbert space, the space of states for your theory. And so that means that we can decompose this commuting action into a sum, or perhaps an integral, depending on just how bad these VOAs are, of representations, modules. So I'll just write it symbolically like this. So you might have to, if there's continua of these modules, then you'll decompose it perhaps into an integral over, you'll have a density of these integral over. So there'll be some multiplicities here, which, so in the discrete case, these will just be multiplicities. And that, in the discrete case, you'll be summing over all simples of M. So for example, in the rational case, there's only finitely many modules for V, and only finitely many modules for this other rational VOA V bar, which often will be isomorphic to V. And so we sum over all of these finitely many simples, and our space has to decompose into a sum of products of these representations. And so it isn't obvious a priori how many copies of each one of these there appears in your state space, so we put down our multiplicities there. And so another ingredient, so part of the story, is to try to understand this decomposition, this reconstruction, if you want, of the full CFT from the chiral pieces. And so the most famous example of this is Capelli, Ytixon-Zuber, around 1986 or so. And they did this for the affine. So when V and V bar are the affine SL2 VOA at positive integer level K. And they found, what did they find? Does anyone remember? They just found an empty list, right? What they found was an ADE classification. So the possible full CFTs corresponding to this choice of chiral algebras falls into it's parametrized, it's naturally parametrized by the A Dinkin diagrams, paths with a bunch of nodes on them, Ds, or the three E's. So the A's correspond to Vestimino-Wittens on the group manifold SU2, a nice compact manifold. The D's correspond to strings living on SO3, another nice compact, not simply connected, but that's more or less harmless, group manifold. The E's, there's three E's. There's E67, E8. One of them corresponds to the SP4 group manifold, compact group manifold. That's the E6. E8 corresponds to the G2 compact manifold, strings living on that. You can reinterpret as having a smaller chiral algebra corresponding to SL2 at some level K, 28 or 10 respectively. And the last one is the only true exceptional here, and that's the E7 one. And that you can think of as triality on SO8, triality on D4, together with rank level duality. So I don't know how to say it. Triality plus rank level duality, level rank duality. Anyways, this is the answer for SL2. And basically for 40 years, not much else was known, but we've crucified the problem now. So if you really want to know your favorite algebra, we can tell you the answer now. So for example, for E8, there's something like, you just have the trivial, you just have the diagonal case with, I think, 2 exceptions. Maybe there's 3, I forget. Anyways, we've crucified this, and the way we got this was using category theory. So it is to that I now turn. So so far I've discussed for rational VOAs, I've discussed things like fusion rules, Verlinda's formula, things like characters, vector-valued modular forms, stuff like that. So I would call all of that, I would call all the stuff on that board up there, I'd call combinatorial representation theory of a rational VOA. And it gets you extremely far. For example, that's all that Capelli-Zubert needed to do the ADE classification. Let's look at a situation that all of us understand far better than representations of VOAs, representations of finite groups. So a finite group representation, let's call it G, your favorite finite group, Z mod 2, or the monster. Finite group G representations. Well, the theory is remarkably close to rational VOAs. So what you have are finitely many simples. You have a semi-simple theory. You have duals. You have a fusion, or it's usually called tensor product. And you don't have characters. But anyways, it's a pretty similar theory. And so at this level, you have characters. So the analog of those characters, those graded dimensions, are the characters of your representation. So you get your character table. In fact, everything here is contained in the character table. So I would say that this is the combinatorial rep theory of your favorite finite group G. So this gets you remarkably far. For almost all purposes, this is all that you ever need. This is all that you ever wished you needed. This is what you wish is all that you ever needed, but almost all the time that wish is granted. But it's not always there. So for example, if we look at the dihedral group D4, so this is the symmetries of the square, and we look at the quaternion group, I'm not sure what it's called. Let's call it Q8. So this is the symmetries, as you know, of the square, and this is the group of unit of quaternions, basic quaternions, plus or minus I, plus or minus J, plus or minus K. It doesn't matter if you don't know what that is, but I'm sure you all know it better than me. These are very different groups. For example, half of the elements of D4 are reflections or involutions, but only one element of Q8, namely minus 1, is an involution. But the character tables are the same. So character tables, what anyone would call combinatorial representation theory of these two groups are the same. It looks like, depending on what you use your rows and columns for, you get this, and you get a bunch of signs. Anyways, the character tables are the same. If you have to figure out how you're identifying conjugacy classes and irreps, but you get the same character table. So the representation theory is not the same. So for example, one of the representations, the two-dimensional representation of D4 sends it sends the rotation by 90 degrees. It sends that to I, 0, 0, minus I. So that's one of the representing matrices. Another representing matrix is the one that you take your favorite reflection. You could send it to 0, 1, minus 1, 0. And together these generate your representation of D4. For quaternions, it's very similar, as you'd expect. You get I, let's say, this order 4 guy, we can send to the same matrix we had before, if you want. And we choose, so minus 1 in this indecomposable representation of dimension 2, the unique one. Minus 1 would get sent to 0, 1, 1, 0. And this is what the representation looks like. So there's different ways to write these matrices, but all of them give you the same determinant. So whenever you have a representation of a group, the determinant will be a one-dimensional representation of the group. In this case, the one-dimensional representation is the identity. In this case, the one-dimensional representation is plus or minus 1. So the determinants of the unique non-one-dimensional, non-invertible representation are different in these two cases. But you can't see that from the character table. It's more sophisticated, the information that goes on. So even to understand the representation theory of the group, you need more information than just the character table, the obvious data here. And the modern way to think about the extra data that you need is category theory. So a slogan that is surely true is that representation theory is just category theory. I'm not saying this is a happy slogan, but I'm saying that this is the slogan. So you can get by very far with combinatorial invariance of your categories, but so in the case of a finite group, you get the category of representations. And so the category of representations will have finitely many simples in it. It'll be semi-simple. It'll have duals, and it'll have a tensor product. But you will not just care about whether two representations are equivalent to each other. That's all you see here when you're looking at character tables, is whether two representations are isomorphic. So for example, minus 1 representation. So all of these representations here, if you square them, you get 1. But in a category, you don't have equality between objects. You have a morphism between objects. So you have to explain. The category stores in it the map, the intertwiner that identifies the tensor product of one of these representations with itself and the trivial representation. So there's extra information there. It's not a lot of extra information. It's not, category of reps isn't that much worse than the combinatorial data, but it's enough to capture the group. So you can identify your group from the category of representations. The category of representations of a finite group is an example, a great example of a fusion category. So not all fusion categories are categories of representations of groups, but anyways, but the other direction does hold. So all of these finite group representations are examples of fusion categories. So you can think of a fusion category, a good way to think about a fusion category actually is categorification of a ring. So I'm sure some of you are very familiar with these words, categorification and stuff, but not all of you maybe are. So this thing looks like a ring because we can multiply and add elements together. Distributivity will be obeyed, stuff like that. And so, but what categorification means is you are allergic to the idea of objects being equal. So when you say that 1 times A equals A in a ring, you can't say that in the categorification of the ring. You have to say there is some map and it's built into, it doesn't just exist, it's there. It's part of the structural data of your fusion category. That 1, the trivial representation, tensored with A, any other representation, there's an intertwiner that maps that tensor product to A. And that's part of the structure of your category. If you could change that in a non-trivial way, you've changed your fusion category. So that's what categorification of a ring means in this case. You don't have equality between elements of your ring like you did before, you have to worry about the actual map that identifies these two sides. But you have no problem with the equality of those maps. I mean, it's kind of a double standard. So, but you can categorize your categorification, in which case you now forbid yourself from also having equalities of these morphisms. So you certainly can't have equality between objects. Any fool knows that, at least from the late 20th century on. But you also can't have equality of morphisms. That would be really naive. But you can have, between morphisms, you'd have to have a morphism of morphisms. But you could have equality of morphisms. So that would be a two category. But of course, you can categorize two categories and get three categories, and you can take the limit and get infinity categories and all that other stuff, whatever. We don't need to do that, thank God. But we do need to go up to one categories. So anyways, that's what a fusion category is. Now, it turns out we're not interested in reps of finite groups. That's too easy for us. We're interested in reps of rational CFTs, or a better way to write it would be VOAs. Now, it turns out that rational VOAs also have semi-simple and finitely many simples, and they have duals and all that other stuff. And so it turns out that the category of representations or modules, same thing, of a rational VOA is also a fusion category. But much more is true for a VOA. A VOA is an incredibly much richer structure than a group. So there's a lot more going on. There's characters. You have representations of SL2Z. In fact, you have representations of all the surface mapping class groups. So much more is true. In fact, there's much more structure, and what you get is what's called a modular tensor category. I'm not going to say much about these beasts, but these are conjectured to be equivalent to the representation theory of a rational VOA. In other words, any modular tensor category, anything that looks like the representation of a VOA, a rational VOA, is the representation of a VOA. There'll be infinitely many different VOAs for which it's the representation theory, so that's not a theorem by a long shot, but we're annihilating obstruction to obstruction, and it's just looking like the gods are pointing us in the direction that every modular tensor category comes from a rational VOA. Anyways, you can think about, I don't want to get into the details of this, but you can think of this as the categorification of a commutative ring. Now, we all know what a commutative ring is. A commutative ring obeys the relation A times B equals B times A. But we're sophisticated. We know that at the categorical level, you can't say A times B equals B times A. You have to specify the actual isomorphism that sends AB to BA. And of course, that's called the braiding. So among other things, although this is pretty much it, a modular tensor category comes with a braiding. And that's how you get your S matrix, et cetera, et cetera. Before I forget, I'll just throw out a couple a simple observation. So can anyone think of a way to go from any commutative ring, can anyone think of a generic way to go from a arbitrary ring to a commutative ring? Is there any way to associate a commutative ring to any ring? The center, right? So given any ring, let's call our ring R, the center, I'm not sure what you want to call this, of R is a commutative ring. So the same will lift to the categorical level. And so given any fusion category, its center will be a modular tensor category. So what does center mean? Well, what does center of a ring mean? Center of a ring means the set of all elements. Maybe I should write this down. So the center of a ring is equal to all elements, let's call it little r. So all elements little r in our ring such that r times s equals s times r for all s in the ring. I think we'd all agree that that's what the center of a ring means. So what's the center of your favorite fusion category? Well, it'll be all objects A in your category, let's call it R, in our category, such that R times S, R fusion S, is the same as S fusion R. But we can't have equalities of objects in a category. What we have to do is also specify the actual map which does this isomorphism here. So in a category, there would be an isomorphism here. You'd have to use isomorphism. You'd put your fusion product or tensor product there as well. And you also have to specify part of the ingredients, the structural data of your center would be, so you're not just going to have your object R, which commutes fusion-wise with everything else, but you also need to choose an actual isomorphism for every element S, every simple object S in your fusion category. And this is called the half braiding, and this data here is called the center of your fusion category. So given any fusion category, we get a modular tensor category. So I'm kind of poo-pooing fusion categories here by saying modular tensor categories are vastly more interesting, which is true. Modular tensor categories are the representation theory of rational VOAs. But fusion categories are also potentially extremely interesting for CFT. So we heard in Masaki's talk a couple days ago that he talked about non-invertible symmetries. So the proper context for non-invertible symmetries should be fusion categories. And so what will take the place of finite groups this century will be fusion categories. So fusion categories are what acts on a quantum field theory, at least the finite things that act on a quantum field theory. And so your favorite fusion category that acts on some holomorphic VOA, whatever that means, is going to give you a new, conjecturally would give you a new rational VOA, and its representation theory would be the center of the fusion category that did your acting. Anyways, there's a whole story here that has yet to be fleshed out, but it's a fascinating story. And so fusion categories are the future groups. So that's what's going to play the role of finite groups in our story. Okay, is that all I want to say? Probably. Oh no, I want to draw a picture. So let's just collect our thoughts here before we get on to log VOAs. So we have a picture. At the summit, we have CFTs, which all more or less equate with VOAs. So it's a complicated thing going to the full CFT from the two chiral halves, but it's doable, and in fact, we've done it. We understand how to do that now. So I would put these at more or less the same level. So this is the summit. At the bottom, we have our categorical. So things like fusion rules, things like modular data. Maybe what contains a bit more information will be the characters of your VOA. And whatever else belongs here. So there's a bunch of stuff here. In the middle, we have our categorical stuff. So our modular tensor category, perhaps our category of defects that are acting on our thing, and equivalent stuff. And so this is in level of sophistication. So if you want to impress, for those of you who are considerably younger than me, if you want to impress your friends, then you want to at least pretend that you're up here somewhere. But there's a cost. And so I think it's fair to say that 99% of the time, 99% of us are down here. You want to be down here. This is where you want to do your work, and it's with reluctance that you rise to handle the other things. But there are situations where you must. And so this is the situation. Actually, there's many of us that are always down here and do perfectly fine. Okay. So let's finally talk about log VOAs. Let's do a calculation. It's going to be an easy calculation because I'm doing it, and it's going to be a not a super careful calculation because I'm doing it. This is a calculation that you can find in any book or review article on CFT. So for example, the big, thick yellow book, DiFrancesco et al. On CFT, you'll find this calculation, probably done unknowingly by the three authors in three different places in this book. And so we're gonna discuss the 2-point correlation functions in a CFT. So don't worry, we're not going to spend much time on this. So let's choose our favorite quantum field, our favorite vertex operator. I'll write it in this way because it's a little bit more concise. This is, I'm going to require that this be a primary. So this just means that the state that corresponds to this, by the state field correspondence, is going to be killed by the Virasoro operators L plus or minus 1 and L naught. It has a well-defined energy. So its energy is going to be called H, let's say. So that's what I mean by a primary. So let's take a field corresponding to a primary state. Okay. Now, if you look at the operator product expansion of our field with the stress energy tensor, what you get is a bunch of commutation relations, which are basic to the theory. I don't think I wrote these down before. So the L's are operators. Anyways, this composition minus the composition the other way is the derivative of your field, L naught, commuting with your primary field, has a similar expression. The details are not important at all for us, but I'll write it down anyways just to impress you with my knowledge of CFT. I need my sheet to get these right. And then there's one for L1 as well, which I'm not going to write down. But it involves, this one involves a W times the partial derivative. This one will involve a W squared times the partial. So again, this is all discussed in all kinds of places, so I don't want to waste our time on this. But you can use these relations to come up with differential equations that the 2-point correlation functions have to satisfy. So our 2-point correlation function, who cares what it means, is going to satisfy, well, from L minus 1, you get that the partial with respect to Z plus the partial with respect to W equals 0. You get from L naught, you get the partial Z times the partial with respect to Z plus W times the partial with respect to W plus you get 2 H's. times your 2-point function. And then you get another one from L1, which is a little bit more complicated. It involves W squareds. And so you get a bunch of differential equations for your 2-point function, which are easy to solve. And what you get is a formula for your 2-point function, which is a formula that all of us, I'm sure, have seen before. Okay. Well, now imagine we're doing a thought experiment again. Imagine that we're in a situation where L naught is not diagonalizable. So of course L naught is diagonalizable, I hear you say. But imagine a situation where L naught is not diagonalizable. So in our VOAs, L naught will always be diagonalizable. We always will have our V being a sum of something like V naught plus V1 plus dot, dot, dot. But the modules for a rational VOA are always diagonalizable, but imagine a situation where these modules aren't. So this is not diagonalizable. So the next best thing will be that we get a Jordan block. So we decompose L naught not into a diagonal matrix. That's what gives us our decomposition into V naught plus V1 plus dot, 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 but into Jordan blocks. And so let's just imagine the simple situation. So we get a Jordan block. We don't get this. We get a Jordan block that looks like this. So the same eigenvalues on the diagonal, of course. But so let's just do a 2x2 Jordan block. And so the first basis vector is going to be our good, wholesome primary phi. And the next one is going to be some partner, some Jordan partner that we'll call psi. Okay, let's just see what we get. Let's do exactly the same analysis and see what we get. Well, you look at how your fields, you look at the OP, you just copy what you did before, OP of this with your stress energy tensor. And what it does is it gives you commutation relations with the Virasoro generators. So you have L minus 1 of our pitchfork. We already know what it does to our primary field. We don't have to redo that calculation. But this one is this. Same as before. This one is the same as before, almost. So it's going to be H pitchfork plus Z partial of psi plus our partner, plus its partner. Did I get that right? And I'm going to skip L1 again. It's a tweaking of the unwritten L1 commutation relation up there. And so exactly as we would have derived those equations over there, we get a bunch of equations satisfied by the various 2-point functions. So the 2-point functions now, there's a few of them. There's our old friend phi phi. There's our new friend psi psi. And there's also the mixed ones, because these operators are going to mix up psis and phis. And so we also have phi psi, and I guess we can also write it down psi phi. So we have 4 different 2-point functions, and we're going to get a bunch of differential equations that these things satisfy. I don't want to waste your time by writing all this down. This you can find in, I'm not sure where you could find this, but some review article on Log-CFT or something. What you get are a whole bunch of equations, and I'll just write down. I think I'm just going to write down one of them. So here's one of them. This will come from L naught. So you get Z. So the L naught equation used to be, it's the second one from the top up there. So it used to be I'm going to apply this to this. So one of the mixed ones, and it used to be 0, but now you get your descendant coming in. Or not descendant, that's the wrong word. You get your partner coming in. And so is what I believe you get. And so that's what you get. And as I say, there's lots and lots of other equations. So you get a simultaneous system of partial differential equations on your 3 or 4 functions, depending on how you count. And you can solve them. They're easy to solve, and this is the answer that you get. Your phi. Does anyone have a guess for what phi is going to be? No. 196,884. So this is one of these miracles that you get the same thing. Actually, you get a special case of the same thing. You get 0. And the mixed one is this. And the interesting one is pitchfork. So pitchfork is somehow less wholesome, less primary than phi. So we expect it to be a little bit weird, and it is. What you get is you get this together with you get a logarithm coming in. Okay? So we're going to see logarithms in our CFT as soon as we have, as soon as we see that L naught is not diagonalizable. Let's do another little calculation. It's going to be a very simple one again because it's me doing it. But I think it's an interesting one. We're going to talk about the symplectic fermions. So this is a theory that exists at c equals -2. So this sounds like a weird value for c. So this is not a unitary theory. A unitary VOA would have to have a positive value of central charge. So this is a non-unitary one. But as far as rational VOAs go, unitarity is nothing special. There's lots of rational VOAs that are unitary, and there's lots that are not unitary. We probably know more that are unitary than are non-unitary, but that's just because of our biases for construction. So things from geometry generally turn out to be unitary. But as we know, you didn't just hear it from me, you heard it from Sergey yesterday, that unitarity is a bias. So it's we surely are many things, but we're not bigots. Actually, we're probably bigots in many ways, but we're no longer unitary bigots. We've learned over the years that we're going to allow ourselves the possibility of non-unitary. So this is obviously a non-unitary theory. It's a very gentle theory. You could basically answer any question. You can answer any question that you want to answer about the symplectic fermions, you can answer. So it's a very friendly VOA. It has the crime of being non-unitary. That's all. So let's work out. So this is going to be a VOA, which means, of course, it has a L naught is diagonalizable for it. There's no worries there. We have something that looks like this. And so, as always, we create the graded dimension, which is erroneously called the graded, it's erroneously called the character. So again, the correct thing to use is one-point functions on the torus. And that's more complicated than you really want usually. So if you specialize everything to 0, then you get the graded dimension. Okay, so this is just going to be, as we know, the sum of the dimensions of the different graded pieces. And you adjust it by the central charge. You have your central charge term coming in, the Casimir effect thing. And then, of course, you have this would be infinite otherwise, so you throw in your variable. And this is what we mean by the graded dimension. And so you can work this out for the symplectic fermions because you can work out everything for the symplectic fermions. It's a very friendly VOA, and you get an answer. And the answer I've written down, and the answer is very nice. So this is our friend, the Dedekind eta. We saw this last lecture. It's one of the basic, perhaps it's the most basic modular form. Very special modular form. We get this. Is there anything slightly interesting or slightly bad about this that anyone can spot? So one thing is this is going to be modular. This is going to have beautiful modular properties because it's built up out of the greatest of all, perhaps the greatest of all modular forms. But is there anything a little bit worrying? Is there anything that's hinting at something a bit sick about the symplectic fermions? Well, I don't know how much you guys know about modular forms. I'm sure some of you know a lot. What's the weight of this? For those that do know, what's the modular weight of this? This is where this comes in. No. What's the modular weight of this? 4. So the modular weight of eta is 1/2. So this is 1/2 times 2 minus 1/2 times 2. The weight of this is 0. The modular weight of this, well, eta has modular weight 1/2. This is a grading on the ring of modular forms. And so eta squared is going to have weight 1/2 plus 1/2 is going to have weight 1. So what we have here, the character of our VOA, the symplectic fermions, is a mixed weight. Modular form. So it is a modular form, but it's mixed weight. Now, the first thing to do when you see the character of a VOA, especially a nice VOA like the symplectic fermions, actually, the first thing you do whenever you have the graded dimension of a VOA is you want to see what happens when you hit it at -1/tau. Because after all, this is what gives us the magical S matrix. And so the magical S matrix should store things like the fusion coefficients and whatever else. It's part of the modular data. It's 1/2, the interesting half, the non-obvious half of the modular data, and it gives you all kinds of other things. So this is the first thing that anyone does. But something bad is going to happen when we do this here. And so, well, I'm not going to work it out because I'll probably screw it up. But this is very easy to work out what the S matrix would be for this thing. Also, another reason you do this is because it gives you the characters of the other characters. It gives you the other greater dimensions for the other modules of your theory. So all kinds of information is hidden in the character of your VOA that you can extract by looking at -1/tau. So it's the first thing that you want to look at. And so if we do this here, we get some answer. And I'm not going to write down the answer, although it's very easy to work out. I didn't write it down. I can't trust myself to calculate it properly here. But what I can tell you is it's going to have to involve taus. So this part will be nice and wholesome. It'll be something like eta. There'll maybe be a 2 in front. So you have your 1/2 in front, and you'll have your eta. It'll be something like 1/2 tau squared over eta tau squared. It's going to be something like this. So this is great. It's what you expect from a VOA character. The problem is over here. What we're going to get is eta. So eta, how eta transforms under -1 over tau is you get this times eta tau back again. So you get some 8th root of unity times square root of tau. The square roots of taus cancel here, but they don't cancel here. So what we get is a tau. We get some irrelevant constant coming along for the ride, but we get tau times a Q expansion. So the S transform applied to our VOA character for the symplectic fermions can't be some linear combination of the graded dimensions of the characters of our modules, because it involves taus. And for any module, its graded dimension, its character is going to be a Q expansion. So something weird is going on here. The span of the characters of our modules is no longer closed under SL2Z. Now, you can think about tau. Remember what Q is. Q is equal to e to the 2 pi I tau. So you can think about tau as up to a constant. Who knows what that constant is, but in principle you can calculate it. It's log Q. So this is the second place where logarithms are arising in a fundamental way in the theory. So for these reasons, these kinds of CFTs, these kinds of VOAs are called logarithmic. So logarithmic VOAs are VOAs where logs appear where logs shouldn't appear, where you wouldn't have expected logs to appear. Okay, so we're going to dive into the story a little bit in a little bit more detail shortly. But let's draw a map of a. I have no clue. That's just some black box that is. You click on it and then it erupts into some complicated words that I don't understand. But I don't know what they're called, symplectic fermions. It's not my word. It's someone else's word that I've memorized carefully. Right. And so, by the way, you might wonder where these taus are coming in. These are the quasi characters that I'll hopefully have a little bit of time to discuss later in this talk. This is what Sergei called the quasi characters. So in these logarithmic VOAs, at least the really nice ones, you augment the ordinary characters of your modules with these things called quasi characters, and that's how you flesh out the modular side of the story. But as I say, we'll hopefully have time to talk about this a little bit later. Let's do a map of all possible CFTs. When I say the word CFTs, generally what I mean are VOAs. So I'm ignoring the jump from the chiral story to the full story. So one corner of the map, a very special corner, but a very small corner, are going to be the rational theories. So these are semi-simple. These are finite. By finite, I mean, of course, the VOA is infinite dimensional. Of course, there's infinitely many different modules because you can take V itself and add it to itself 67,000 times. So of course you have infinitely many different modules, but you only have finitely many simple modules. And you have only finitely many indecomposable modules for that matter. So it's semi-simple, finitely many simples. Everything is nice and modular. And you know the story. Everything works out beautifully. It's extremely rich. There's a number of examples, which I'll write in chalk, which looks different color to me, but probably looks the same color to you. But that's one of the advantages of being up at the board, is you get to see the different colors of chalk. And so we have lots of examples of these things. One are the bosons on a torus, compactified on a torus, bosons on a torus, or what you could call what I would call the lattice theories, because that's what you use to compactify your Rn with. You have the Westermino-Wittens on compact Lie group manifolds. You have Virasoro minimal models. Conjecturally, if you choose any rational VOA, you choose any finite group of automorphisms, and you look at the fixed points of that group of automorphisms, then you get a much smaller but still rational theory. So that's proved now for solvable groups, but for other groups it's not. The moonshine module is another example, et cetera, et cetera. So there's a number of examples, but they're boring examples in the sense that they're classical examples. So they're, at least in hindsight, they're obvious constructions, coset construction and orbifolds and stuff. They're straightforward, well-understood constructions applied to a very few well-understood examples using very classical math. And these generate all of our examples right now of rational VOAs. So this is a problem, a bottleneck in the theory, because we don't know what things are true. You don't care about proving that something isn't nearly as important as knowing what's true. And the problem is, if you don't have very many examples, or you're not sure that you have enough examples, you don't know what's true. So you know it's true if you actually manage to prove it. But so it would be really, really, really helpful to have new constructions, to have new families of examples that are sort of sufficiently non-classical. So if string theory or geometry or whatever somehow manages to get you, or Sergei's work is going to point us at some potentially interesting new examples. So that's the theory really, really, really needs. It will stagnate without that. So we need some interesting, more examples of rational VOAs, CFTs. But we expect this to be a pretty small corner of the map of all possible CFTs, but it's going to be an extremely rich corner. It's like the map of all possible Lie algebras. Well, the most special of all Lie algebras probably are the finite dimensional semi-simple ones. These are ones that have a very rich structure. They have fingerprints all over. Arguably, they're the most boring class of examples, but that's because we live 100 years after Lie algebras were invented. And so we're nowhere near 100 years after the invention of CFT. So this is still an interesting class of examples. There still are some interesting questions. For example, fixed points of a rational VOA, is that still rational? So, so this is a very special corner. Maybe it's especially boring. That depends on your personal taste. So these are unitary or non-unitary. All of these are unitary or non-unitary. Okay, and then we also have things like the free boson. So I'm not sure what to call these. So we'll call these semi-simple. I don't know if there's a name for these. Semi-simple, but infinite. They may or may not have modular. So examples are free bosons. So here, as we saw, there's uncountably many simple modules, irreducible modules. They all look pretty much the same, but technically speaking, they're different. So that's a pretty boring example where you do have some sort of modularity. A more interesting example would be the Westermino-Wittens on non-compact things like SL2R, where it's a semi-simple theory. Everything where things are under some control, but it's pretty darn complicated. So there's been some work on these kinds of things. So this is semi-simple but infinite. So I guess we're having this row is semi-simplicity, and this column will be finite. and this column will be infinite. So we have what you could call log rational theories. Or another word that's used, I'm not going to have time to get into why it's called this, but these are called C2 cofinite VOAs. The reason is because to any VOA, you can assign certain quotients. And so you have your VOA quotient, some subspace. And one of these quotients is the C2 quotient. For various reasons, it's called that. And so when it's finite dimensional, then you have, when it's, the thing is called C2 cofinite. And so these are the same as log rational things. So what we have here is semi-simple, not semi-simple. And so L naught is not semi-simple. L naught is not diagonalizable. So we get log stuff coming in. But it is finite. So by finite here, I mean that it has finitely many simples. Unlike the free boson, it has finitely many simples. And so some examples of this are the symplectic fermions. And we have some kind of modularity, but it's a bit weaker. I shouldn't say it's, well, okay, it's a weaker modularity, but it's a little bit more complicated. So it's modularity, but it's a little bit more complicated. You have to introduce these quasi-characters to get your modularity. So the symplectic fermions are a good example. Another great example are the triplets. The triplet algebras is called WPs, where P is greater than or equal to 2. And there's very, very few other examples. This is the interesting corner, I would say, of the map of all CFTs at this stage in our development. So here you can say a lot of the basic questions have been worked out. This has incredible structure. This has almost as much structure, but almost everything is still to be worked out. And so this is a very interesting corner of the map, but it's extremely small. We have very few examples here. So this is poisoning our development of this area, is our lack of examples, especially in this corner here. So the triplets correspond to SL2. So they're kind of like, they're one of these rank 1 kind of a thing. And so you're expecting there to be analogs of the triplets, whatever this means, the triplets for all SLN, the B series, E8, et cetera, for all the Gs. You're expected to have analogs of these things. So they'll be defined by Drinfeld-Sokolov reduction, that kind of stuff. And so we're expecting there to be lots more families. It should more or less echo what's going on up here, but we have very few examples. And then over here we have what I guess you'd call the generic CFT. So the generic CFT are beta gamma ghosts. So these are infinite, non-semi-simple. So that means L naught is not going to be semi-simple. L naught is not going to be diagonalizable, so they're going to be logarithmic, and they may or may not have modularity. So in general, a generic example of a generic CFT will be hopeless for all time. No humans, if Martians turn out to be a lot brighter than us, even they won't be able to really understand the generics, the truly generic CFT. But there's some special examples where they're important. They have some role, for example, in string theory. We can say a lot about them. And there's lots and lots of examples of these things that we know about. So the Vestamino-Witten at fractional level are generic CFTs. So the Nappy-Witten on the Heisenberg group, H4, has been played around with quite a bit. And I think I'm forgetting some other examples. Super WZW. And there's lots and lots of other things that can be included here. This is the map of all CFTs, map of all VOAs. So, well, this is very small. This is, right now at least, extremely small. And so you have a blob of them. Almost all of them live here. Almost all of them are logarithmic. These ones are non-unitary. These ones may or may not be unitary. Okay, let's look a little bit closer at the symplectic fermions. Sorry, say that again? Yeah, I would guess. I've never looked at them, but I would guess that they're generic. I'm not. I shouldn't say. So I don't know. For me, I've looked at this in this column is where I've done the work that I've done has been restricted to that. So. Okay. Sorry, I can't hear that. Oh. Okay. So let's look at the symplectic fermions in a little bit more detail. So as I said before, this is almost our only example of a log rational theory. So in what sense is this? So we know it's not rational because it's behaving inappropriately. It doesn't obey it doesn't have the S transform doesn't work right. So the symplectic fermions are a supersymmetric theory. So let's look at their modules. So their modules are, I'll call it V plus minus. So V plus is the even part. Our VOAs here, I've avoided supersymmetric VOAs just to keep things, relatively narrow. So our VOAs are bosonic. So when I say symplectic fermions, I mean the even part of this supersymmetric theory. So the even part of the supersymmetric. So most people, when you say symplectic fermions, you really would mean the supersymmetric version. So we have the even and the odd. And then you have something that I guess I'll call W. So this is the even or odd twisted symplectic fermions. And this is it. Those are the simple or the irreducible symplectic fermion modules. So let's write down the fusions of these fusion products. So of course, the VOA, it acts like the unit in our fusion rules. It's in our category, it's the identity, always. And so, so I don't have to write down the fusions of V plus with anything, but I'll write it down anyways. So V plus or minus, let's call it V alpha. So alpha stands for plus or minus. Tensor V beta, plus or minus, is going to be V alpha beta. So the param-Frobenius eigenvalue of these things are going to be ones. So this is invertible. This is a simple current. So this thing tensored with itself is equal to 1. So this thing, when we fuse it with everything, is going to permute the different things. And so we see that with the next tensor product. So the twisted ones tensored with the untwisted ones, it's going to be twisted, of course. So of course, for alpha equals 1, it's identity. For alpha equals minus 1, it permutes. I don't need to write down W fusion V because this is braided. So the fusion rules are commutative. And so if I tensor, so the big thing left is to tensor fusion W with W. And what we get is, what should we get? Can you guess? You guys are good at fusion rules, I'm sure. What's the obvious guess for this? Sorry? Yeah, that's a good guess. It's embarrassingly wrong, though. So what we do is we leave the world behind. So these are not closed under fusion product. This is another symptom of a logarithmic theory. So in a rational theory, of course, everything is closed under fusion because everything it's semi-simple. It's a semi-simple theory. So anything that you get, tensor product of two modules is another module, and so it has to decompose into the simples. But we don't have a semi-simple theory. So if this did decompose into simples, then that would mean it decomposes into a certain number of copies of V with a certain number of copies of W. Then it would be a semi-simple theory because this is all of the products. So it can't. It has to involve something new. And so it's involving something that we'll call P. We'll have more to say about P next. So you never get, so your fusion rules will never be closed in a logarithmic theory, unless you make it closed. So you can make it closed by doing the Grothendieck ring. So the Grothendieck ring would take any non-simple thing appearing here and replace it with all of the composition factors, all the simples that this is built up out of. So as you know from the quiver lectures that we saw, we're running out of time, so I'll speed this up a bit. So maybe I should say something more about P. So one thing you can say about P is, I'll just write down P plus and P minus. You just change pluses to minuses and minuses to pluses. So P plus, I'll write it, so the way that you have a Louvy diagram for it. I'll explain what this means in a second. So this is the sense in which everything is built up out of simples. So it's built up out of simples in the same way that our quiver things, so you have these upper triangular decompositions or writings, interpretations of your representations. And the things on the diagonals of your upper triangular thing, I'm using the picture that we used in the quiver talks. The diagonal ones are simples, they're simple modules, and the off diagonals are the extension part that tells you how. So here, what this means is that this thing is a submodule of, do I have this? No, I have this wrong. This thing is the submodule. At least this is the way that I draw them. So maybe other people have the opposite convention, but this is a submodule of P plus, And the quotient of this submod of the big thing by the submodule is this thing. And then this thing, so that if we do the same for this thing has this as a submodule, and the quotient of this thing with this submodule is this. So the subquotients, so if you look at submodules, do quotients of the big thing with that, then take each of those pieces that you got and do the same, or keep repeating, you eventually get down to simples. So taking quotients of submodules eventually gives you down to x plus, x minus, x plus, x minus. Who cares the order? These are called composition factors. And so anytime you have a module, you always have composition factors. Your composition factors will always be simple. And so for this thing here, this thing that I'm calling P, you get this, and it'll be, when you have a minus sign, you just change the sign of all of them. And so this is how your module decomposes, but it's indecomposable, so it's not the sum of these things. It involves non-trivial extensions. Okay, you should all know about that, or you don't care. And so that's that. What else do I want to say about this? I should also say, to finish off the story, I should say what happens to P's. So what's V alpha tensor or fusion with the P's? Well, as you know, V is going to has to act like the identity. This is just going to be P's again. And what's the W's tensored with the P's? Well, this is going to be, make sure I get it right. These are going to be twisted. So we get two copies of W plus and 2 copies of W minus. And then we fuse these P's together. They're called P's for a very good reason. And what we end up with is a similar story. We get the P's back again. And so if you include these P's, then you get something that is closed. I don't know if this is a theorem for all log rational VOAs, but it's certainly expected to be true. So what the P's are projective covers. So P, so the algebraic meaning of P is it's called the projective cover, and I'm running out of time, of the V's. So projective cover means it's a projective module, whatever that means, which has this thing as its quotient. So it's a cover of this thing. And it has a submodule, which is whatever it is, and the quotient of this by that submodule is this thing. And the projective cover of every object in these categories will have a projective cover, and it'll be unique up to isomorphism. So that's what it is for these things. The projective cover of the twisteds are the twisteds. And the conjecture, it might be a theorem by now, but certainly the guess is that all the simples in a log rational theory, the simples are not closed under fusion, but the simples together with their projective covers are closed under fusions. In a rational theory, every simple is its own projective cover. So one of the main differences, algebraically at least, between the log rationals and the rationals is that the role of simple module, irreducible module, is split up into 2 roles. Half of the job that simple plays in the rational story is covered by the projective covers, and the other half is is played by the simple module itself. So, so and what else do I want to say here? I should probably say something about these quasi characters. So the problem with it's very hard to get at what you need in order to. It's very hard to get at any normal definition of character or greater dimension isn't going to see the off-diagonal bits of these upper triangular modules. So normal traces are just going to see the diagonal components of it. So it's just going to see what you'd see in the Grothendieck ring. So in the Grothendieck ring, what the Grothendieck ring does, it just replaces this with with its composition factors. So it'll be 2 copies of X and 2 copies of X. Sorry, X, these are V's. So that's what the Grothendieck ring does, and that's all the characters would see. They'll never see the fact that we have a P here. They'll never distinguish P from 2 copies of V plus and 2 copies of V minus. And so to get at the quasi-characters, this is the work of Miyamoto. He used a trick from positive characteristic representation theory where you have semi-simple theories and you can you have to modify the characters that you'd get there to see the off-diagonal bits. And so he just carried that over into the VOA world, and he got these quasi-characters, and I don't have time to get into this. So I think we're understanding now, from a more physical standpoint, what this means. So right now it looks kind of foreign from the physics point of view, but I think we understand what's going on at the physical world. So, okay, what else have I forgotten to say? Well, I should very briefly say, okay, so these aren't the only modules of your symplectic fermions. So you have all kinds of other modules for your symplectic fermions. In fact, there's continua of it. In fact, in terms of quiver language, the modules for your symplectic fermions contain as a subset the modules for this quiver, which we looked at a bit in the last couple days. And so you have continua of indecomposable modules for the symplectic fermions. So you have buckets and buckets of modules for this. This was not at all the case in the rational case. So even for the simplest log rational VOA, you have continua of indecomposables. So once again, all of them are built up from the simples. You just extend in continua of different ways, but so the Grothendieck ring won't see this, but these modules are there. Very, very, very few of these play any role in the CFT, it seems. So I'm not sure why. So really the CFT sees more or less just these things. The V's, the W's, and the projective covers, the simples and the projective covers, and then some of the subquotients thereof. So I don't know of any example where any other of the uncountably many modules of the symplectic fermions, for example, plays a meaningful role in the CFT. So, and the final thing I want to say is, how do you get the full CFT from the chiral algebras, from the VOAs, when you're not in the rational world, but instead you're in the log world, the logarithmic world? So this will be the final thing that I say. And so this is starting to become understood. And so what it would look like for the symplectic fermions is, this is the world of coends, if you know anything about that. And so the space of blocks for a rational full CFT, as you know, would look like, in this case, if the symplectic fermions were rational, then the state of the full space would look like some combination of V's tensor V's, and V's tensor W's, and W's tensor V's, and W tensor W's with various multiplicities. That's what you'd get. You'd get the direct sum of these. And so in the Grothendieck sense, that's what you get. Of course, that's all you could ever possibly get. But if you don't semi-simplify everything by going to the Rothenberg quotient, then what you get is this. There's different ways. So what you get is this. You get projective cover times V. And I'll put a bar on top to remind us that this is the other side. This is the holomorphic, and this is the anti-holomorphic, right moving, left moving, or whatever. I guess this should be left and this one right. This will be P minus tensor V minus, and this will be W plus tensor W minus, and this will be W, sorry, I got this wrong. This will be W minus tensor W minus. And you can also write this in the other order. It should be the same thing. And that is, so that's what it's going to look like here. So basically, it's going to be the simples with their projective covers. That's the kind of structure that you have. This would be a diagonal. This would be the analog of the A's in SL2. This is sort of the diagonal version. And so there's also going to be some off diagonals, and I'm not sure how that would look. So the answer should be coends. So this is how to get the full from the chiral. It'll look something like this in general. I think that's all I want to say. That's all I have time to say anyways. So.
Standard case, so you start from Chern-Simons theory, and you look at what happens at the boundary.
So you're saying I should what?
Because you mentioned WCW
yeah.
at some fractional level, so I was
right.
wondering whether you have also Chern-Simons interpretation of this type of theory.
Yeah. So Chern-Simons. So that's outside of my area of comfort. So I know that fractional level Westermann-Witten is pretty unpleasant. So at the beginning, like 30 years ago, I think people thought that it would be a gentle generalization of the integer level, but things go wrong. All kinds of things go wrong, and so it's a very complicated theory. So I don't know what the physics of it looks like, and I don't know how sick it is as a physical theory. I can't really say anything about that, unfortunately. I mean, it's certainly worth wasting some time on. Yeah, I should stop there, or I'll start saying things that are stupid. But so some of the people that have done work on this are there's a whole pile of people. So David Ridout. So this is fractional level. I think the breakthrough in this happened with a paper about 10 years ago, or more than 10 years ago, by Kreutzig and Ridout on the more physical side, and a little bit before that by Adamovich, and probably miscellaneous collaborators on the more math side. And so until then, it was pretty naive what people were doing here. And so so we understand things that look like Verlinde formulas for this case, and yeah, so when I say fractional level, generally what's meant by this is admissible. And yeah, that's a story that I haven't been following much, but there's been a lot of work on it in the last few years. So, but the physics of it is pretty. I should also mention Gabriel. So Gabriel was the first to point out that the initial guesses of people were really naive, and then Kreutzig and Ridout and Adamovich, fleshed out that a lot further. So that's all I can say, really. Sorry.
functions on the worksheet. There is a worksheet with the columns, and there is a worksheet with the disk. So I was thinking because of the open disk, for instance, the vertex, since we have a boundary, we have like some relation between the automatic and the multi-sectors. Because here you didn't mention any relation between the two sectors. So I guess we are working in the case where we have like Log-CFT, so this closed string point of view, and open string point of view, that will sort of change.
Yeah, so yeah, it's a good question. So yeah, so there's a whole boundary CFT world, which is more fundamental than, probably more fundamental than the open string world here. So as far as the connection between the two halves go, I'd say the fundamental. So the physics side is a side that I can wave my hands, but that's all I can do. If I start probing, like shining a flashlight on it, then things start to get a little bit fuzzier. So I can't really say much about that. There's no extra relation between the two. So the right way to understand the full CFT connection. So if, for example, let's just deal with the rational case, which is a little bit simpler. So the rational case, I write down expressions that look like, for example, in the diagonal case, you'll have your simples arranged nice and neatly. So the way to really understand what's going on here is through the open string. Sorry. So there's a so my picture is a categorical picture, this relationship, but the categorical picture comes from the open string. And so that's really where you understand this full CFT relation. So the answer to your question is that's where you get the connection between the two. But it's contained in the story that I've described when I write down these kind of things. So the partition function, so really what's going on, so writing down this kind of an expression isn't sufficient. This is kind of the combinatorics of the full CFT. What's really going on is you have your left-moving VOA, chiral algebra. You have your right-moving VOA. And in order to get your full CFT from this is the information. This is a way to interpret the information in the open string, all the information in the open plus closed string. What you need is 3 pieces of information. So your full CFT is captured by 3 pieces of information. Really, this is an insight that came from Moore and Zyberg back in the 1990s or 1980s or something. There's 3 pieces of information. One is you maximally extend your chiral algebra. So in the Capelli-Itzix and Zuber classification, you in the D series let's do the E8 one. In the E8 one, let me state what's true, and then I'll just specialize to the Capelli-Itzix and Zuber case. So you maximally extend the left chiral algebra, and you get something that we'll call VL extended. You maximally extend the right moving, you get something that we'll call VRE. These are true ordinary boring VOAs. These will be rational VOAs in the rational CFT setting. And then they have their own categories of modules. These will be modular tensor category, and they have to be equivalent as categories. And so the 3 pieces of information is this equivalence, which will be some kind of a tensor functor, whatever that means, and then your extended VOAs. So you have to specify what your extension VOA is, the extended VOA is, and specifically what this functorial equivalence between their categories is. And that's what you get mathematically speaking from the open string. So this is story. So this picture here is the full story for a CFT. This is what a CFT is, mathematically speaking, categorically speaking. And the picture comes from the open string. So just to tidy things up, so in the E8 exceptional of Capelli, Itzix, and Zuber, you have the VOA that you start with has to be an SL2, affine SL2 VOA. It's going to be SL2 at level 28 for both of these. That's what you're starting with. That's what they're classifying. And so you extend this to a G2 VOA at level 1. And that's what you get for both extensions. And the functorial equivalence is the trivial one. So the triple that you get in that case is identity and G2 level 1, G2 level 1. And the same goes for any VOAs. So when we say that we've classified all full CFTs for your favorite choice of these affine VOAs, affine chiral algebras, then that's what we mean. We've classified all triples. And again, that picture comes from the open string. Yeah.
So you mentioned that one of your motivations is to go beyond something clear, right?
Yeah, yeah.
And try to discuss
Yep.
something more exotic, something new. Now, on the other hand, let's see. It seems that for some cases of logarithmic theory we discussed, people try to use the customalistic story, and then there is a small quantum group, etc.
Yep,
So
yep.
in the end, it seems that people finding the algebra structures come back to that story. So I wonder how to incorporate this.
Yeah, so there's the Kazhdan-Lustig story. So for those of you who aren't familiar with it, in the Westermino-Witten story for positive integer level and compact groups, then the Kazhdan-Lustig story would be that the category of representations you get for those VOAs are the categories that you get from quantum groups at roots of unity. So so that's sort of the basic baby case of Kazhdan-Lustig. But then you can look at some of these weird things like triplet algebras, these triplet algebras, and you can ask the same question: are they the category? So there's a theorem that says that any modular tensor category, or more generally so the categorical version of these log rational theories would be braided finite tensor categories. So they're just a generalization, a non-semi-simple generalization of a modular tensor category. So there's a theorem that says that a non-semi-simple or a semi-simple modular tensor category always comes from some Hopf-like algebra. So it can be a Hopf-like algebra that doesn't have that much structure. It's not a Hopf algebra. Because that would require integer dimensions. It's a weak quasi-Hopf algebra. So a totally useless device, but it's a much simpler beast than a VOA. And so there's a theorem that says that you always have this Hopf-like algebra that realizes your category of representations. Now, in all the cases that we've looked at, we either don't know what that Hopf-like algebra is, or it's going to be a boring one. I shouldn't say boring, but one that is connected to Lie theory. So. Yeah, I think that in 10 years, if I give if I'm invited back, I hope I haven't done so terrible a job that I won't be invited back. And so let's pretend in 10 years I'm invited to give a similar lecture on it. Then I'll talk about the explosion of work in Log-CFT and all these incredible families that physicists have found and the mathematicians are finally agreeing with. Yeah, and so then my guess is that there's the majority of rational and log rational VOAs have no direct connection to Lie theory or finite groups. There's some empirical evidence. The evidence is categories are simpler than VOAs, and so we can actually construct categories. We can construct modular tensor categories, and we're finding that there's many more modular tensor categories than that. There's lots of these that don't come from Lie algebras or finite groups, at least not by any construction that we know of. And so if you guess that if your category looks like it comes from a VOA, then it does come from a VOA, then these will come from VOAs that presumably have no obvious connection to Lie theory, or at least they're new constructions that we don't know anything about. So things like the Hoge group is the most famous example, but there's lots of others. So I myself have constructed hundreds of these categories that are exotic in some sense. But we don't have any VOA construction for these. But it just looks like of the categories, maybe most of them are exotic in this sense. And so it's tempting to guess that most of the VOAs are exotic too. We just are too dumb, or we're too early in the development of the theory to see it. And once again, it's physicists that usually come up with the good ideas here, and you guys have forgotten that exotic can be interesting. No, there's no. Yeah, so there's no, that's right, that's the problem, is that you're going up in complexity, so it's always harder to reconstruct in that way. So you could do things like, so you can look at the comment, so we all work in the comment, so you can look at things like, it's easy to, so there is machinery, really effective machinery for coming up with the vector valued modular forms for these categories. You can look at the whole group. The whole group is really a fusion category. So what you do is you look at the center of the whole group and you get a modular tensor category. And you can write down what the vector valued modular forms, what the character vector is for the whole group double, for the center of the whole group. It's easy to do, and you get your set of possibilities at C equals 8. There's 2 possibilities that are there. And on and on you can go. So we're good at that. But just knowing the Q characters of these things doesn't mean that you have a VOA that underlies it. In fact, recently I've shown that these can't be realized by a CFT at C equals 8 or C equals 16. You have to go at least up to C equals 24 to get the whole group VOA. It can't exist smaller than that. And so what you can do though is that kind of stuff, like the combinatorial type stuff or even the categorical type stuff, we understand now quite well. But then there still is that final step. And so we're not good at that yet.